So let's get started. Now, in the previous lecture, we have already started our discussion on oscillation, right? When we have shown that the general solution to the equation of simple harmonic motion. Okay, this is a simple harmonic motion, and we say that initially we say that it can be fitted with a cosine function, and we have also shown that the equation of motion, the general equation of motion of the simple harmonic motion, we assume a mass tied to a spring, which obeys Hooke's law, and in this case, we have the frequency, the frequency omega naught of the oscillation being equal to k over m square root, where k is a force constant and m is the mass of the object. And then we assume the solution of this form. We assume the solution to be of the form of either cosine omega naught t or sine omega naught t. We find that both of them satisfy the equation. Okay, we find that when you have cosine and sine, you do two derivatives. It just go back to itself with a factor of minus omega naught square coming out. But that exactly satisfies this equation. So both the cosine omega naught t and the sine omega naught t, they are the solution to the problem. And because the equation is linear, the linear combination of the two solutions is also a solution of the problem. And in fact, we have mentioned to you that this linear combination of a sine and a cosine is in fact the most general solution to this problem. Now, this general solution contains two undetermined constants, and these two undetermined constants are to be determined by the initial condition. Now, but before telling you how to insert the initial condition into the formula, we first change this form of the formula into another expression. We convert this into another expression, which is also a general solution. These two solutions are in fact equivalent to each other. Now, so you can express the solution in terms of a linear combination of a sine and a cosine, and with the constant c and d. But you can also write the solution as the amplitude multiplied by a cosine, but the cosine omega naught t contains an initial phase. The initial phase is called phi. Okay, so here the undetermined constants a and phi. Okay, so both solutions contain two undetermined constants, and they can be converted from one to the another. So the two solutions are actually equivalent to each other. They do not have any difference. The difference is that is a form. If you write it in this form, you may find it easier for you to fit the initial condition in certain situations. While if you write in other form, you may find it more convenient to fit the initial condition in other situations. So it depends on your choice. There's no rule which says that you use this or use that. They are just equivalent. Now let me before going further, let me assume what this phase factor phi means, because this phase factor will appear very frequently in our subsequent discussion, especially on force oscillation and also in waves. So because this factor appears so frequently, it is instructive to have a more detailed discussion of it before proceeding further. Okay, so let's understand what is it meaning before going further. Now, the general solution can be written in this form. A is of course the amplitude. The amplitude is amount of vibration, right? It's a degree of vibration. It measures how much the vibration is. So this is actually the maximum displacement of the particle from the equilibrium position. So that is A, right? Now, if I set the phi equal to 0, if I have no initial phase, then this solution is just A cosine omega naught t, which is just a mass tied to a stretch spring and stretch it and release it from rest. This solution we have seen before at the beginning of our discussion, right? So it goes like this. It goes like oscillation. with a period state. I call it T. And now, so what would happen if I add a phase? Okay, what would happen if I add a phase? Now, I claim that when I add a phase, the original expression without phase is that I have a first peak. Now, the cosine function is grabbing up and down, right? So there are peaks and trunks. If I want to locate the peaks, I will find that the first peak is exactly located at t equal to 0. So when the time is 0, the displacement is at the first maximum. It is the initial position where the block is released, right? Now, but I would like to ask a question. If I now add the initial phase, then where will be the peak? Now, I claim that the peak still corresponding to the argument of the cosine b equal to 0. Because this cosine function is maximum when its argument, when the total phase inside is equal to 0. So that means the first peak for phi equal to 0, the first peak is of course t equal to 0. But if I have a phi, then the first peak is still identified by the fact that this bracket, the guy inside this bracket is equal to 0. Okay. So that corresponds to what? Where? That corresponds to omega naught t plus phi equal to 0. So the first peak position has been shifted. It's no longer at t equal to 0, but is at what? At where? It is equal to t equal to minus phi over omega naught. Now, if I assume that in this diagram, I assume that phi to be positive, then t equal to minus phi over omega naught is a shift of the first peak to the negative direction, because there's the negative sign here. So that amounts to a shift of the first peak from 0 to a certain point in the negative x direction, negative t direction. So how much is this? Let me be more clear. I can convert this omega naught into the period. The omega naught is 2 pi over the period. So I now find the position of the first peak in terms of the period t. I find that the period, the new position of the first peak is located at the time equal to minus phi over 2t over 2 pi t, capital T, which is here. Okay. Now let's take a closer look of this. It's quite interesting. Phi over 2 pi multiplied by t, the period. Now, I know from our elementary understanding of the trigonometric function that 2 pi is a complete cycle of the cosine function, right? Whenever you change the argument of a cosine by 2 pi, it just goes back to its initial value, right? So 2 pi is the cycle of a cosine function. And when you add a phase, phi over 2 pi, it means a fraction of the cycle. Okay, if phi is equal to 2 pi, that means 1 cycle. If phi is equal to pi, that means half of a cycle, and so on and so forth. Okay, so it's just a fraction of the cycle. And for each cycle, there's a period, right? The time for the particle to oscillate 1 cycle is exactly 1 period, right? So this is actually the fraction of a period. Okay, so if you have a phi inserted into here, that means your peak position will be shifted by so many fraction of a period. Okay, by phi over 2 pi of a period. That is the meaning. Now, so it is useful to memorize some special angle. For example, if you have phi equal to pi over 2, if you have phi equal to pi over 2, then phi over 2 pi is what? Phi over 2 pi is 1/4, is a quarter. So you have the peak shifted to the negative t direction by a quarter of a period. And in that case, initially, if you don't have the phase, initially the first 0 is here, right? The first 0 for the oscillation is here, but now it's shifted to the negative side by a quarter of a period. That means that the 0 position will go to here. Will go to the 0 point. Okay, so it will shift by a quarter of a period. Now, if phi is equal to pi, then pi over 2 pi is 1/2. Then the curve will shift by half of a period. Okay, and of course, if phi is equal to 2 pi, then the whole curve will shift to the left by 1 period. Now, this is the initial position. Now, if the initial position depends on the choice of your 0, we choose the time to be 0 to be here, or you will choose the time to be 0 at another position. That depends on your choice. So if you insert a phase vector phi here, that means initially you are not talking about a 0 phase. You are talking about a phase of phi, okay, specified by this phase vector. Okay. Now, so this diagram is drawn by assuming that the phi is positive. The phi is positive, meaning the curve is shifted to the negative t direction. If you have a phi that is negative, then the curve will be shifted in the opposite direction. It will shift in the positive t direction. Okay, and by the same amount, you take absolute value and you calculate this amount, and this is the number of period that you have shift. Okay. Now, so with the solution given by this, now we know that the phase is sometimes quite arbitrary. It depends on your choice of a 0 time, right? If you choose, for example, for this oscillation, if you choose the 0 time to be here, then you don't have the phase, right? But if you choose the 0 time, not at the peak, not at the first peak, but somewhere here, then you have this expression. Okay, so so for the oscillation, you can see the phase phi is actually quite in some situation is quite arbitrary. So to facilitate our discussion, we may first neglect the phi. So we assume that the block is released from rest at time t equal to 0, and that result in a cosine curve. Okay. Now, so with this displacement, we can find the velocity by a straightforward differentiation. Okay, the velocity of the object is simply a differentiation of the displacement, and the cosine now become a minus sign. And by the chain rule, we have an additional factor of omega naught coming out. And I can also find the acceleration by differentiating the velocity once more. And so the sine will become the cosine, and I have an additional factor of omega naught again. So totally, we have 2 factor omega naught and a minus sign. So we have minus omega naught square a cosine omega naught t, right? But I notice that a cosine omega naught t is just x, right? So I can write this expression as minus omega naught square x. Now, but what is this? The acceleration equal to x multiplied by minus omega naught square. It is nothing. It is only the differential equation of motion, right? This is the equation that we start with. The a is a second derivative of x. On the right hand side, we have x multiplied by minus omega naught square, right? This is just the equation of motion that we start with. So it's not surprising to get this equation back. Okay. Now, but I want you to notice one thing. Now, for the oscillation, the displacement changes a cosine, but the velocity changes a minus sign, and the acceleration changes the minus cosine. Now you see the acceleration and the displacement, they are proportional to each other, but they are just in the opposite direction. Okay, so this is a property, this is a very special property of the simple harmonic motion. Whenever you see a motion with an acceleration proportional to the displacement, but they are in the opposite direction, that is a simple harmonic motion. The solution to that problem is a simple harmonic motion. It's an oscillation in a simple harmonic term. Okay, so this is a very special property for simple harmonic motion. And in fact, whenever you see this equation, you don't have any doubt, you can write down the solution immediately. It must be a simple harmonic oscillation with a frequency omega naught. Okay. Now let's go to the phase now. When I have x and I differentiate, I get the v, right? The cosine become a minus sign. Okay, so the cosine is this curve, but the minus sign is this curve, right? The sine curve is originally going positive, but since there's a minus sign, you flip it upside down, and so this becomes a minus sine curve. When I differentiate one more, it becomes a minus cosine curve, the minus cosine curve, which is something like this. Okay. Now, an interesting thing to note is the following. Whenever you differentiate a sinusoidal function, like for example cosine, you can see it's changed. The first change is from a cosine to a minus sign. But if you look at these two figures, it just amount to a shift in the curve to the negative x direction by a quarter of a period. Now this is a period. So a quarter of a period is like this. Is this length. Okay. If I shift the curve to the negative side by a quarter of a period, a cosine curve will become a minus sine curve. Can you see that? And then when you differentiate once more, it amounts to shifting this velocity curve to the left, to the negative x direction by another quarter of period. So now the first trunk is here, right? It is a quarter of the period. This is a quarter of a period. And when you differentiate once more, this peak, this trunk will now shift to the 0 point, will now shift to a 0t position. So it amounts again to a shift of a quarter of a period. So when you have a sine or a cosine, when you differentiate once, it will shift the whole curve to the negative side by a quarter of the period. Okay, so that is an interesting thing to know. Now, the second thing to note is the amplitude for the velocity and the amplitude for the acceleration. Now, it's very easy to remember the amplitude for the velocity and acceleration. Why? For the displacement, the amplitude is a, right? A is the length. When you multiply the a, the length, with a frequency, you get the dimension of a velocity, right? Because the omega has a dimension of second per second, right? The radian does not count because the radian is dimensionless. So omega has a dimension of per second. So A has a dimension of meter. So this combination has a dimension of meter per second, which is the dimension of velocity. And in fact, this combination is the amplitude for the velocity change. This is the maximum velocity actually. And if you multiply another factor of omega naught, that becomes omega naught square A. And the dimension of this quantity is meter per second squared, which is the dimension of acceleration. And in fact, this quantity is actually the amplitude for the acceleration. This is the maximum acceleration during the motion. Okay, so it's easy to remember. You have the amplitude, you multiply 1 omega naught, you get the maximum velocity. You multiply 2 omega naught, you get the maximum value for the acceleration. And if you start for any sine or cosine function, you differentiate, you shift the whole thing by a quarter of a period. You differentiate again, you shift again by a quarter of a period. Okay, so it's quite easy to remember. Now, having learned that, let's us discuss about energy. Since we have the displacement and the velocity now, we can calculate the energy quite easily. The energy consists of two parts. The potential energy, this is an elastic potential energy due to the stretch spring, right? The spring is stretched, so it has elastic potential energy. And also because the block has a velocity, so it has a kinetic energy. And so we can calculate the kinetic energy and the potential energy from these two expressions. The potential energy is half kx squared. That is the potential energy of a spring. We learned it in chapter 5, right? So we just substitute this x into the equation, and we find that the potential energy of the spring, it goes as half Ka squared cosine squared omega naught t. Okay. Now, it's interesting to note that the energy goes at the square of the amplitude. It is not directly proportional to the amplitude, but it's proportional to the square of the amplitude. Now, this is a very general feature. It's not specific to this kind of oscillation. In fact, you will find that eventually in most of the oscillation, the linear oscillation that you learn in this course and also in a senior course in mechanics, you will find that the energy, no matter it's potential or kinetic energy, they both have an energy proportional to the square of the amplitude. Okay, it's not proportional to the amplitude itself, but the square of the amplitude. Okay, now this fact does not confine to mechanical oscillation. Even for electromagnetic oscillation, the same thing holds. You know the intensity of light, right? The intensity of light is the power of light you receive on the surface per unit area, right? And the intensity of light, because light is a EM wave, so it depends on the electric field and a magnetic field. It is electromagnetic oscillation. And you will find that the intensity of light is actually proportional to the square of the amplitude of the electric field. It's proportional to E0 square, where E0 is the amplitude of the electric field. Okay, so again, the intensity or the energy proportional to E square, the proportional to the amplitude square, but not to the amplitude. Okay, now how about the kinetic energy? It's also proportional to A square. How can we know that? We just substitute this expression for V, and we find that the constant is half m omega naught square A square sine square omega naught t. But we recall our definition for omega naught. Omega naught square is actually K over M, right? This is the definition of omega naught in our spring mass system, right? So M omega naught square is just K. So it just becomes half Ka square sine square omega naught T. Now, so you can see the U, the potential energy and the kinetic energy, they both have the same amplitude. They both depends, both of them have the maximum value of half Ka square. But one varies with a cosine square and the other varies with a sine square, and they are both always positive. Okay, but if you add them up, because the cosine square and the sine square added together is 1, the total energy is half K square, and that is constant. Against the time t, you will find that the potential energy is the blue curve. So it's varies something like this, and the kinetic energy is varies sine square, so it's varies something like this, and the sum of the two curves, it becomes the horizontal line. It becomes the total energy, which is always constant. Okay, so that is the physics of the problem. Now we are ready to match the initial condition now. So let us assume that initially the block has by initially we in a t our time t equal to 0, we have the initial displacement of the block at x0, and initially we have the velocity as v0. So the naught here, the 0 here, or the subscript indicate the initial value of the position and the velocity. Okay, now so we may find more convenient at first to match the solution, to match the initial condition with the solution of this form, the combination of a cosine and sine. Okay, now I emphasize again that this solution is completely identical. It's equivalent to the solution with an amplitude and an initial phase. So a sum of a cosine and a sine with the same frequency is just nothing, but just shifting the peak of the cosine to with an initial phase. Okay, so it just amounts to adding the sine and the cosine curve up to form another sinusoidal curve, but with a different initial phase. Okay, so it's nothing. Now, so I differentiate. When I differentiate, the cosine become minus sine with omega naught. The sine become a cosine again with omega naught. Okay. Now, so I match the initial position now. Initially, t is 0. So the sine term has gone because sine 0 is 0 and cosine 0 is 1. So I only have c. But my initial condition is that the initial position is x0, right? So that means xc is equal to x0. Simple. How about the velocity? The velocity is given by this expression. And when time is 0, the sine term is 0, right? And the cosine term is 1. The cosine factor is 1. Okay. So I only have omega naught d, which is equal to the initial velocity v naught. So I can solve for d. D is just v naught over omega naught. So I have the full solution now. Simply c equal to x naught and d equal to v naught over omega naught. This is the full solution. And this solution is general. It can apply to any initial condition, any x naught and any v naught. Okay, we just substitute our initial condition into here, and the solution is there. Okay. But I want to challenge you with another problem. How to set the initial condition for this guy? Instead of writing it as a sum of a sine and a cosine, I now write the solution as the amplitude and with the initial phase. So can you take a few steps? It's not difficult. You just differentiate x to get v, and you fit the initial value, the time, namely the time t equal to 0 of these two guys, x and v, to these two initial condition, and see if you can solve the resulting equation for a and phi. Okay, let's give you 5 minutes to do it. Do you think you can do it? You take out a piece of paper and try. Okay. If you learn the answer, if you know the answer, please do not hesitate to let me know. You just type something on the chat box, or you can just unmute yourself if you like. Yes, I have some. Let me see. Um, This is almost correct. I think your solution, Hangyu, your solution almost correct, but your dimension seems to be wrong. I see. I see you are correct because of square root. the square goes to, yeah, you are correct. Yeah. You write like latex, so so it's difficult to see the actual formula from the code. Anybody who got the answer? No, I don't think you are correct because you find the A in terms of X and V. X and V are not constant, right? A and phi are constant, right? So you should express A and phi in terms of all the constant given in this question, with namely X naught and V naught. Is that right? Now maybe let's do it together. Now we have X, so V is just a straightforward differentiation of X, and that is minus omega naught A sine omega naught T plus phi. So at time T equal to 0, I just put 0 in this expression, right? And so I got what? I got for X, I got A cosine phi is equal to X naught. And what? And in fact, I find Chen Junwang's solution is almost correct, except you have to solve for, I think you have to solve for the two expression. So when I put T equal to 0 here, I got minus omega naught A sine phi be equal to V naught. Okay. Now, so the problem is how to eliminate one of the variable. We have two variable now, A and phi, right? But we have to solve each of them. How to eliminate one of the variable? Now, the easy way to do it, if I call equation 1, this is equation 2, the easy way to do it is to divide equation 2 by equation 1 to get rid of the A. So if I do it, it becomes what? It becomes minus omega naught tangent phi equal to V naught over X naught. And then we have the angle phi be equal to arctangent V naught over minus omega naught X naught. So this is the phase angle phi. But how do we solve for A? Now it's easy because we can make use of the identity that's sine square phi plus cosine square phi is equal to 1. So I square the equation and I move all the constant to the other side and I employ this identity. So X naught divided by A square plus what? Plus V divided by omega naught A square is equal to 1, right? So I can solve for A now. I move the A to this side and take a square root, I think I find that A is equal to X naught square plus V naught square divided by omega naught square. So this is my answer. Now, although the expression is a little bit more complicated. Now you have the arctangent here and your minus sign here, but they are solvable in principle. But it would be simpler to write in this form, right? For this form, you can fit the X naught and the V naught very easily. But for this form, you have to calculate the A, and you have to. But when it comes to the situation where you want to find the amplitude of the oscillation, then you need to do this. Okay, you need to find the amplitude oscillation by using this formula. Okay. Now I have some video for you to see. I think I find that very interesting. It demonstrates a simple harmonic motion. Now there is a bell, a rolling bell, automatic bell, and there's a simple pendulum here. The simple pendulum has a funnel here, and the funnel is holding some sand. So during the simple harmonic motion of this funnel sideways, the sand will leak out and it traces out a curve. And due to the rotation of and due to the motion of the belts, there will be a XT graph showing the simple harmonic motion. Let's see it.
All right, here at the Exploratorium, they have a pendulum. Pendulum swings back and forth in simple harmonic motion. Well, this is no ordinary pendulum. This is a pendulum into which we can pour sand. And if we pour sand, it's going to fall onto this table. Watch what happens.
Now, so that becomes an XT graph. The oscillation is the displacement.
To create a wave pattern.
The bell naturally gives you a sense of the time, right?
Simple harmonic motion.
It helps you
the
trace the variation of time.
Is a function of the pendulum. The energy of the pendulum produces the energy in the waves. Distance between waves is a wavelength. Amplitude of a sound wave is a function of loudness. Of a light wave, the amplitude is a function of brightness. The frequency of this wave is a function of the pendulum's period of oscillation, and it's determined by the length of the pendulum and the planet we happen to be standing on. Can't change that. In this display, we can see that the circular motion produced by the round.
Now, this is a circular motion, a uniform circular motion, okay? Now, but when a uniform circular motion is projected onto a plane, now projecting this onto the plane amounts to shedding some light on this pillar. And so the shadow goes through the wall here. And when this pillar is undergoing circular motion, its projection onto the wall will be a simple harmonic motion. Now let's see how.
Object.
Now we can adjust the pendulum such that both have the same frequency. So they oscillate to and forth by the same time with the same period. So they go.
So we're getting pretty close.
And
the pendulum
they swing
motion,
forth and back
the shadow
with the
of
same
the
period.
rotating object are almost lined up now. The frequency of oscillation for a pendulum is a function of its length.
Now this pendulum have slightly different length of suspension, so that's so they have a difference in the frequency or the period. Okay, so you can see when they are displaced and released together. Originally, they have rather close. They gather quite close together because they almost have the same period. But as time goes on, you see the difference between the vibration will become larger and larger because they actually have different periods. So there will be a cycle. You can see that they will be turning out of phase and then will be in phase again to vibrate together again. But that takes quite a long time. Now let's see.
this deflexant.
Now you see a difference now. Some of them are vibrating faster and some of them are being slower.
The shorter ones swing faster, the longer ones swing slower, giving us a pretty cool demonstration of pendulum motion. Now there's certain mathematical relationships between these frequencies, obviously. A function of length and the acceleration due to gravity.
Now so you see,
mass really doesn't.
they are just out of phase, right?
Interestingly enough.
Now after some time, they will be in phase again.
And they
you see?
appear to line
they
back
align
up
again. And then they will go out of phase, and whole thing will repeat.
Pretty cool, huh? I really like this. This is good.
Okay, so this is the demonstration. Now, before having a break, let me introduce to you another example of a simple harmonic motion, and that is the simple pendulum. Okay, we have studied this problem before, but we haven't solved it exactly. Now, we use the Newton's law of rotation. We use Newton's law of rotation. A simple pendulum amounts to a ball suspended by a string of length L. The string is attached to the wall, attached to the ceiling at one end. And so the angle theta is the angle that the string makes with the vertical direction. Now, so in terms of this angle, now because we only have a problem with the only variable is the angle theta. The length is kept fixed. So the velocity of the pendulum will be equal to length of suspension multiplied by the angular velocity. The angular velocity omega is the rate of change of this angle. So omega is d theta dt. And the linear velocity going in this direction, the tangential direction, is just the length of the suspension multiplied by the angular frequency. V equal to R omega, or in this case, L omega. Now let's apply the Newton's second law for rotation of this form. First, we want to find the torque. The torque is, of course, due to the force of gravity. Now, the force of gravity is vertically downwards. So I have a vertical downward force of mg. But in order to calculate the torque about the fixed point, I have to multiply the weights by the perpendicular distance, which is this horizontal distance now. The horizontal distance between the ball and the vertical line is L sine theta. So mg multiplied by L sine theta become the torque. Now you notice that I put a minus sign here. Why? Because in my figure, I define the positive direction as the increasing direction of the angle theta. So when this object moves sideways, it moves up, the angle increase, that is a positive direction. But the torque now is turning the object in the opposite direction. It is tending to degrees theta. So that means it should be given minus sign. Okay, so because it tends to decrease the angle. Okay. Now, how about the angular momentum? The angular momentum is simple because now the velocity is perpendicular to the radius. So the angular momentum is just mvl. Okay, mvl. Linear momentum multiplied by the length. Okay. And in terms of the angular variable, V is L omega. So I have ml square omega. Omega is d theta dt. So I have the angular momentum as ml square d theta dt. Okay. Now we put the angular momentum here into this equation, and that amounts to differentiate once more. And so the angular momentum differentiate once more, the derivative acts on d theta dt, and that become the second derivative for theta respect to t, right? So that is on the right hand side. On the left hand side, I have the torque. The torque is given by this. So I write down. Let me rearrange the equation for easy for the ease of manipulation. So I move all the constant to this side. Okay. The m cancel, one of the L cancel, And so the second derivative of the angle with respect to time is minus G over L sine theta. Now, this equation is difficult to solve. It is solvable analytically, but difficult. You have to solve the angle theta as a function of time in terms of some special function known as the elliptic function. The elliptic function is a difficult a mathematical function which you haven't learned before. Now, I'm not going to teach you those difficult functions because they are beyond the scope of this course. But I think you can solve it numerically. You can solve it with a spreadsheet. Even if the angle is large and this acceleration depends on the sine the angle, you can still do it numerically. And that's exactly one of your projects. I think some of you have already been assigned this project to find the oscillation of a pendulum with a large angle. So I anticipate your doing of this project, and I anticipate your seeing your result. This is what you're going to do. Now, but for our discussion now, we are interested in a small angle. Suppose the angle theta is small, and that means the sine theta is almost equal to theta. And of course, theta is in radian. For this equality or for this approximation to hold, the theta must be expressed in radian. Okay. Now, so if the angle is small enough so that I can replace the sine with a theta, then I can solve this equation simply. Okay, because this is a standard form of a simple harmonic motion. The acceleration being proportional to the displacement. Although the acceleration now is not d squared dt squared, it is in terms of the angle theta, but still this is the acceleration and this is the displacement. And the proportional constant is the negative constant, right? There's next sign here, and this is the constant, right? So I can rewrite the equation in this form. I define omega naught squared as G over L. And so this is just a standard form of SHM. And the frequency of the oscillation is G over L square root. Okay, I can see from this comparing these two equations. And the general solution, I don't need to do it again to prove it again. I can immediately write down the general solution. The general solution is this: the amplitude A and a cosine omega naught t, and with an initial phase phi. Now, in particular, if the pendulum bob is released from rest as a maximum angle, the amplitude equal to theta m, then the initial phase phi is 0, and the amplitude is just theta m, and so I have this solution. Okay, this is just a solution we have seen before at the beginning of our discussion. Okay. So let's have a break for 10 minutes. And after that, we will be back for. Okay, let's continue now. Okay. Let's go back. We haven't been able to got to the point of damped oscillation yet. Before that, we will talk about the generality of simple harmonic oscillation. First, we will talk about the simple harmonic oscillation with a constant external force. Now, what is a constant external force? A constant external force may be the force of gravity or any other force. Now, in the beginning of our lecture, we neglect gravity, right? We assume the broad spring system to be placed in a horizontal table without friction, so that the oscillation is performing horizontally. Okay, but now we can assume the whole thing to be in the vertical direction, so that the block is under the force of gravity. Okay, now under the force of gravity, what will change? The first thing is the initial position. Even without oscillation, the spring is stretched by a small amount due to the weights of the object. Okay, so how much is a stretch? If I denote the unstretched position of the spring by this level, when the block is at this level, which is called the equilibrium level, at this level I call 0x, the spring is unstretched. So when I release the ball gently, it will stretch the spring by an amount of x0. Okay. And by the equilibrium of force, because now the mass is at rest at this position. So by the condition of equilibrium, I have the weights of the object be equal to the force of the spring. And since the extension x0, the force of the spring is kx0, and the two forces balance each other. Okay. And so I can solve for x0. x0 is mg over k. It is just a downward shift of the equilibrium position from the unstretched position. Initially, without gravity, this level is the unstretched position, the equilibrium position of the spring. But now, because of gravity, the equilibrium position has shifted downwards. It has shifted downward by a distance of x0. It's due to the weight of the object. It stretched the spring by a little bit. Now, how about if I stretch it further? If I stretch the spring further, that would be restoring force, right? The spring will try to pull my block back, and I can set the equation of motion now. Now, the first two terms for the equation of motion is the same as before. It just says that the mass multiplied by the acceleration is equal to the net force. The net force now consists of the force of the spring, which is minus kx. This is the same as before, but now I have a downward force of gravity. And the downward force of gravity tends to pull my block in the positive x direction. So I have a plus sign here. Okay. And if I divide by whole equation by m, I got this equation. Now there's a constant term that cannot be solved by the standard way. So I have to find ways to get rid of this constant term. This is a constant acceleration due to gravity. Now how to do that? There's a simple trick. Instead of counting all the displacement from this level, which is the unstretched position of the spring, I now would like to count all the displacement, to measure all the displacement about the new equilibrium level, which is the position, the equilibrium, the new equilibrium position of the block. Okay. Now, when I don't have gravity, this is the equilibrium position. But now, since I have the gravity force balances the force of the spring at this level. So I should measure every displacement with reference to this level. I define a new variable called Kc. Kc is measured from this level, from the red level. And x is measured from the blue level. So the difference between x and Kc is the constant, which I call x0. So that means Kc is defined by what? The key is defined by x minus x0. So this is a simple transformation of Kc and x, and they're just different by a constant. The constant is the initial downward shift of the block. So x0 is mg over k. So I write back. Now, if I differentiate both sides with respect to time, because the second term here is a constant, so it has gone upon differentiation. So the second derivative of x and the second derivative of Kc, they are just the same. But how about the right-hand side of the equation? If I convert the x to Kc, then I would have x be replaced by Kc plus mg over k, right? Instead of writing x, I write x as Kc plus mg over k. Now you immediately see a good thing. Here I find that after canceling the m and canceling k here, there's a minus sign that goes with the g. And so the minus g will cancel with the plus g for the last term, right? So I would be able to get rid of all the constant. And eventually I got minus k over m Kc. So if I measure everything from the new equilibrium position, then namely I express everything in terms of Kc, then the equation of motion exactly reduces to a simple harmonic motion. So again, in terms of Kc, since the motion is simple harmonic, I don't need to solve it again. I can quote the standard solution. Kc is a cosine omega naught t plus phi. If you want, you can change it back to x. The difference between x and Kc is just a constant. So I add a constant mg over k back to the cassie, I find my x back. Okay, so there's just a shift in position. There's no change in frequency. The equilibrium position shift, but the oscillation remains the same, and there's no change in frequency. Now I would like to discuss about generality of simple harmonic motion. You may wonder why we study such a trivial system. The system we studied seems to be quite trivial. It consists of a spring, a mass attached to a spring. Not normally in our daily life, we don't bother with the mass attached to a spring under oscillation. We don't bother with that, right? This is only a toy problem, just for physics illustration. It's not a daily life problem that we are going to encounter in our daily life. But I'm going to show you that, in fact, most of the oscillation that we encounter in daily life, whenever the amplitude of the oscillation is sufficiently small, they can be approximated as simple harmonic motion. Now, this statement is rather general. It does not only apply to a spring mass system or even a pendulum. It applies to almost every form of oscillation, including, for example, molecular oscillation. You know that the solid molecule are bounded together by the van der Waals force, but they are led to vibrate about the equilibrium position. And when you add the heat, when you increase the temperature of the solid, they just vibrate more violently, and the average distance between them increased, and that is a thermal expansion, right? That oscillation, if the oscillation amplitude is small enough, they can still be regarded as a kind of simple harmonic oscillation. So that's why we want to learn it, because it's so general. It can be applied to many different physical systems. Now here we should understand why this is so by considering the potential energy function. By using a suitable approximation for the potential energy function, we will be able to show you that, in fact, most of the oscillation we encounter can be simplified as simple harmonic motion, if provided that the amplitude of oscillation is small enough. Now let's define this more precisely by using mathematics. Now suppose there is a position of stable equilibrium. If you plot the curve of the potential energy against the displacement, and if you have a stable equilibrium position, it exhibits itself by a minimum in the potential energy curve. So the minimum potential energy, position in the potential energy curve correspond to the a stable equilibrium position. And we have already discussed in chapter 5, if you slightly displace the object either to the left or to the right of this position, there will be a force. The force will try to pull it back to the equilibrium position. So you imagine if you now displace the object either to the right or to the left and release it, it will simply goes on and oscillate between on the two sides to a back and forth above the equilibrium position. So that results in a simple harmonic motion if the amplitude is small enough. Okay, so we are going to solve this problem. Now we will first rely on Taylor series to find an approximate expression for the potential energy function U about the equilibrium position. So let's do the Taylor series. And if you remember, in our mathematical supplement, we can explain any function U as long as this is a smooth function. We can expand the function about a fixed point x0 by using the Taylor series. The first term is the function you vary at the fixed point, which is now our equilibrium position x0. The second term is the derivative of U at that position multiplied by the first order change, x minus x0. And the second term is half of the second derivative at that position multiplied by the difference x minus x0 squared, and so on and so forth. I have the higher order term, but I neglect it. Okay, so I approximate U in the close vicinity of the equilibrium position. Okay, now this expression is only correct when my x is sufficiently go close to x0. If I'm getting farther away, then the approximation may not work well. Okay. The equilibrium position corresponding to the force equal to 0, right? That is the condition for equilibrium. But the force is the first derivative for the displacement, for the energy. Okay, the force is minus du dx, right? And minus du dx at the position of the equilibrium is 0, because this is a minimum in the energy. So its first derivative is 0 there. Okay, and this is of course true because the force is 0 at the equilibrium position. So that corresponding to a 0 slope of the potential energy curve, and that's a minimum in the potential energy curve. Okay, so the first term, the second term has gone. I don't have this term, and so the u now become a constant plus half u double prime x minus x naught square. Okay, so the dependent on x goes to this term, goes to the term with the dependent x minus x naught square. Now, if I want to find the force, I would differentiate the u with respect to x and add a minus sign. The constant term has gone, and the second term, when I differentiate with x, the 2 here will cancel with the 2 here, and after differentiation, I only get 1 x minus x naught, and then with a minus sign, because the minus sign come from here, come from the minus du dx. Now, so let us write down the equation of motion. By Newton's second law, the mass times acceleration is the force, and the force now given by this, right? Now, so you can see this is essentially simple harmonic motion. We do the same trick as before. Let's change our variable. Instead of writing the equation by x, we would like to write the equation in terms of the c variable, which is x minus x naught. So if I replace x minus x naught by c, I just replace this term by c, and the second derivative of x and the c are the same. So I get the what? I get a simple harmonic motion equation. And of course, the constant here is the square of the frequency. Okay, so immediately I can write down the solution. The solution in terms of c is just a cosine omega naught t plus phi. If you like, you can make everything in terms of x. That is just amounts to adding a constant x naught. And the frequency for the vibration omega naught is simply the square root of this constant. So it's equal to the square root of u double prime at x naught divided by m. Okay, so let's resolve the whole problem. Now I want you to see more pictorially or more visually what we are actually doing. Now a general potential energy curve may be like this. It may not be so smooth. It may not be symmetric about the equilibrium position. It may not be a very nice curve. But as long as I'm getting very close to here, suppose now I'm very close to this equilibrium position, I can approximate the originally very complicated potential energy curve by a quadratic function. And the quadratic function looks like this: u naught plus half k x minus x naught square. When x is close to x naught, I can always choose a k such that my red curve, which is a parabola, is very close. We'll be getting very close to the real potential energy curve. Okay, but that approximation is possible only in the vicinity of the equilibrium position x naught. Okay, so what is the k? Well, the k is just the u double prime, right? If I replace the equation of motion of the previous problem if I replace the u double prime by k, I just get back the spring mass system. Okay, so we are using a spring mass system to approximate a general oscillation. If the force constant of the spring is now, now becomes the second derivative of the potential energy curve, that will be a good approximation to that oscillation, and we can solve the oscillation just like a spring mass system. So this is the idea behind. But remember, this is possible only when my oscillation is small. If my oscillation is very large, then the potential energy curve here may deviate a lot from the quadratic curve, and so my approximation will not hold well. Okay. Now let's do a simple example. Suppose we have this potential energy curve. Now how to sketch it? We sketch u against x, and when x is small, the exponential term can be neglected because when x is 0, the e x minus kx is almost 1. So it goes downwards as a straight line with minus x. But eventually, the exponential term will dominate over. And the exponential term, it has a minus kx here. So it dies down exponentially. It dominates over the x, and eventually it goes to 0. So in between, there must be a minimum, right? There's a minimum, and that minimum is the equilibrium position, the stable equilibrium position. And we want to find oscillation about this equilibrium position. And how do we do it? We find the derivative. We find that the derivative of the u, this is a straightforward calculation. I think you can do it yourself. And after doing the calculation, I think we have kx minus 1, the exponential function. Now you can immediately see where the equilibrium position is. It's corresponding to the point where u prime, the slope here, is equal to 0, or the force here is equal to 0. And that corresponds to kx minus 1 equal to 0. And that is x naught is equal to 1 over k. That is the equilibrium position. So we label the equilibrium position here by 1 over k. Let's go to the second derivative. I use the product rule to differentiate this product again. And after some algebra, I will not to go into the details here. I think you can follow it yourself. And that becomes something like this. This is a second derivative. But according to our rules, we have to find the second derivative at the position of the equilibrium position, which is 1 over k. So I substitute 1 over k to here and here to find u double prime x naught. So x here is replaced by 1 over k, and the exponential function, the x is also replaced by 1 over k. And I got 2 minus 1, which is 1, and this is e to the power minus 1. So I have k e to the power minus 1. So this is my u double prime, e over x naught. And the equation of motion goes like this. The solution is evident. I do not need to write again. And the frequency is u double prime x naught divided by m square root. So I just put it here, back to here. I got the frequency. Okay, so everything is quite simple. You just identify the correct terms, and that is the result. I don't know if you have encountered this potential in your high school study. This is called van der Waals potential. Van der Waals potential is the potential energy between two neighboring molecules or neighboring atoms. Okay, when two molecules are in a solid, two neighboring molecules in a solid, they have a small attractive force, and the small attractive force is given by the second term of the van der Waals potential. Now you can see this van der Waals potential actually has a very strong dependence on distance. It has and for the second term, which is attractive, you can see a minus sign here. It goes with a distance as 1 over the distance to the power 6. So when the distance increases slightly, the force actually decreases a lot. Okay, but when the two atoms or molecules are getting very close, there is a strong repulsive force here, which is characterized by this potential, which is A over R to the power 12, which is even more sensitive to distance. Now, this is a very strong potential, and that happens because of the Pauli exclusion principle. When the electron cloud, you know that the atom or molecule, they are made of outermost shell electron and also the atomic nucleus, right? So when the outermost shell electron of the molecule and the atom, they are trying to squeeze together when the two atoms approach each other. The two electron cloud would tend to overlap. And the Pauli exclusion principle says that the electron are fermion, the so-called a special kind of particles called fermion. They do not like to be squeezed. to the same energy state. And if you do so, they will exert a strong force, a very strong force to oppose that. That's called Pauli exclusion principle. And you can explain it only from point of view of quantum mechanics. Okay, that's a quantum phenomenon. But nevertheless, even if we don't know how to do this in quantum way, we know that the potential energy essentially goes like this. So you can see a potential energy curve to be like this. At first, I have a strong repulsive force if they go very close together. But when in the long range, I have a small attractive force. So in between, there must be a minimum in the potential energy. And the minimum potential energy position is the position when the two particles are separate. It's an equilibrium separation of the two particles. But there may be small oscillation about that position, and that motion can in fact be described by simple harmonic motion in just the same way as here. If you are able to find the U double prime at the equilibrium position for this potential, you will be able to estimate the oscillation frequency. And that is a beautiful thing, right? Now, then we can proceed further to discuss about damped harmonic oscillation. Now, in our first model, simple harmonic motion, we only have include the spring that provide the restoring force, right? But now we have damping. The damping is what? The damping is some kind of friction or some kind of resistance that oppose the motion. So how would we model that? We would like to model that with such a simple relationship. We assume some kind of viscous force, such that the damping force is proportional to the velocity. Okay, so the minus sign is here to indicate that the damping force is opposite to the motion, opposite to the direction of motion, opposite to the velocity. But the magnitude is proportional to v, proportional to velocity, and the proportional constant is some constant b. Now, in general, we have seen that for air resistance, even for air resistance, this relation may not hold well. For large body and for body moving at high speed, the resistance force may go as minus b v to the power n, where n is typically around 2. Okay, we have the drag force, right? We have the air resistance, air drag. But let me make it simple. Instead of assuming a very complicated model at the very beginning, let me assume that the drag force is proportional to v, so that the equation of motion become easily solvable. Now, this is not a realistic model in some situation, but it makes the equations solvable, easily solvable. That is an important point. Now, so let's put this drag force into the equation of motion. So the first two terms are the simple harmonic motion. The last term is the drag. Okay. Now I divide the whole equation by the mass m, and become something like this. And for convenience, I define the parameter b and over m as alpha. This is just a shorthand for this coefficient. And k over m, as usual, I define it as omega naught square. Okay, this is a simple harmonic motion frequency square. Okay. Now this is a second order differential equation because it's contained the second derivative. It contains the first derivative. It contains x itself, and all the coefficient of this term are constants. Omega naught square is constant, alpha is constant, the one that goes before the second derivative also constant. So I call this a second order differential equation with constant coefficient. Now there are standard methods for solving this equation in mathematics, but we would try to solve it in a physicist point of view. We will guess a solution. Now, what kind of motion should we expect? Now, because this is there is a restoring force, so we still may anticipate some oscillation. So the oscillation may be there. So we may have a cosine term or sine term that exhibit the oscillation. But there is a damping. But when the damping is weak, we expect the object to oscillate many times before coming to stop, before slowing down, right? So there will be oscillation that's superposed on a decay in amplitude. You will find oscillation, but the oscillation will be smaller and smaller in amplitude as time goes on, and eventually comes to a stop. That is what we expect, and it's for small damping. For small damping, we call it weak or light damping. Okay. So let's guess a solution. We expect some oscillation, so we have a cosine term with a frequency omega 1. Now, notice that this frequency omega, we label it omega 1, which is different from omega 0, which means that with damping, the new frequency may not be the same as the old frequency. Damping may affect the frequency. That is what we suppose. Okay, let's assume in general we have omega 1 instead of omega 0. So when the system is damped by the external force, the frequency does change. Now, but the amplitude will decay with time. How do we describe that? If we describe that by adhering a exponentially decaying factor, e to the power minus gamma t, where gamma is another constant to be determined. Now you can see because of this minus sign, the amplitude, when the amplitude multiplied by the e of this exponential, this factor will decay with time. Okay, now so the new solution have two parameters, gamma and omega 1, while the equation of motion has another pair of parameters, namely alpha and omega 0. So in order for this to be a solution to the problem, this solution must satisfy the equation. And since two parameters in this two equation, this two parameters may somehow related to the original parameter in the equation. So these two set of parameters are related. I should be able to find gamma and omega 1 in terms of alpha and omega 0. If I put this solution into the equation and I require the solution to satisfy the equation, I will be able to find this relation. Okay, so this is my goal. My goal is to show that this is in fact a solution by direct substitution into the equation, and then to find gamma and omega 1 in terms of alpha and omega 0. Okay, so this is an educated guess. Before solving for physicists, before solving a difficult problem, we will have some guess and try it to see if it's work. Now, how to solve it? How to prove that this is in fact a solution? Now, the procedure is rather complicated because it involves this equation involves the first derivative and the second derivative, right? So we should write down the first derivative and the second derivative. But the differentiation is rather complicated, right? Because x consists of two factors, the multiplication of two factors, right? When I differentiate, I use the product rule. When I differentiate once more, I have to apply the product rule again. But I would anticipate the answer of this form. Why? Because when I differentiate this guy, I use the product rule. The product rule consists of differentiating either the exponential function or the cosine. If I differentiate exponential function, the cosine will be there, right? The exponential function doesn't change apart from a constant. And if I differentiate the cosine, the exponential function of course will be there, but the cosine will change to a sine, to a minus sign. And of course, there's another constant coming out. So I will expect after the first differentiation, the dx dt will compose of two terms. One corresponds to have a cosine and the other one with a sine. The coefficients are known. I have to work out this coefficient. So I leave it blank here. Okay. Now, originally for x, I only have the cosine term. So this is 1, and the sine term has 0 coefficient. I just write it for completeness. And so this is 1, this is 0, right? And after one differentiation, you should find the new coefficient for the cosine and the new coefficient for the sine. And after two differentiation, I still expect the dependence to be like this, right? Because when I differentiate sine and cosine, just go to the other one. Cosine becomes sine, sine becomes cosine. Exponential term doesn't change the exponential. So the answer is still in this form. Now I would like you to find out the coefficient. Can you do it in say 4 minutes? Okay. Now, in fact, this is not new to you. You have done it. You have done it in where? You have done it in in the homework of, I think, the homework of chapter 1, right? I told you to do it, right? So you just give me the answer, or you do it once more. But for me, if I were you, then I would like to write some shorthand. I'm just very lazy. So for the exponential factor, I prefer to write as E. And the cosine, I just write as C. And for the sine, I write as S. So I write X as E multiplied by C, which means as exponential function multiplied by the cosine. Sorry. And this I call it S. Can you see that? So what is dx dt? I differentiate the E first, but when I differentiate the E by the chain rule, I got a factor of minus gamma, right? So I have minus gamma E. The exponential factor doesn't change, right? Except now I get a factor, extension factor of minus gamma. How about the C? When I differentiate the C, it becomes what? This cosine becomes minus sine. And I have additional factor of omega 1 coming out. So I have minus omega 1. It becomes a sine. So let's write better. I will have E minus gamma C minus omega 1 S. Is that right? So I now will what are these coefficients? This is 1, this is 0. And here I have minus gamma that go with the cosine and minus omega 1 that go with the sine, right? How about the second derivative? When I differentiate the E, I apply the product rule. I got another factor of minus gamma. I go back to here. Okay. And then I leave the E unchanged and differentiate this once more. When I differentiate this once more, the cosine becomes minus sine, right? And it gives me another factor of omega 1. Cosine becomes minus sine, the minus sine gone. So it becomes S. The minus sign cancel with the minus sign in front. And I just got an additional factor omega 1. And for this term, the sine become a cosine. And I get another factor of omega 1. So I have omega 1 square. It's becoming like this. Now let's tidy it up. For the coefficient with the cosine, I have gamma square here, right? The minus sign cancel, I have gamma square. Here I have minus omega 1 square. That goes with the C. And for the sine term, what do I got? Minus gamma multiplied by minus omega 1 is just gamma omega 1. And I have another gamma omega 1 here. So I now have 2 gamma omega 1 that goes with the sine. Is that right? So I now have the coefficient for this. For the cosine term, I have this coefficient, gamma square minus omega 1 square. And for the sine term, I have this coefficient, 2 gamma omega 1. Okay, so that is my answer. Okay, I got it all, but by just a simple differentiation. Now you notice that after I do it in shorthand, I save a lot of writing. I would be able to do it in just 2 minutes, 2 or 3 minutes. But if you write out all the sine and the cosine and exponential function, that amounts of, that would be a long time. So you see the essential of the problem is very, very important. You don't spend extra time on the unnecessary stuff, but focus on what is important. That is a way to solve a physical problem. Okay. Now, after I work out the coefficient, then what should I do? Now here I just copy this answer once more. I have to satisfy this equation. Now, but the cosine and the sine, they cannot be made equal, right? They cannot be made equal at all times. A cosine omega 1t cannot be equal to a sine omega 1t for all the time. But in order for this to be a solution of the equation, they should be at the sum of the two, the sine terms and the cosine term must be equal to 0 for all time. And that means the coefficient for the cosine and the coefficient for the sine must be equal to 0 separately. So if I gather from this equation, if I gather all the coefficient for the sine, they must be equal to 0. And if I gather all the coefficient for the cosine, they must also be equal to 0. That is the only way to make this equation satisfy for all time t. Otherwise, they cannot be satisfied for all time t. Because the sine and the cosine, they are not 0 at any time, right? So in order to make them 0, the only way to make them 0 is to make the coefficient 0, but not to make them 0, right? So, but the sine and the cosine, they are just two different functions. And in order to make them both 0, you have to make their coefficient both equal to 0. Okay. So I collect all the coefficient for the cosine. Now the cosine term goes like this. Now, for the second derivative, I'm gamma square omega 1 square minus omega 1 square. Alpha multiplied by dx dt. So I have alpha multiplied by minus gamma as a second term, right? And I have omega naught square multiplied by x. So I'm omega naught square multiplied by 1. Okay. These are the cosine term coefficient. They added to 0. And how about the sine? For the second derivative, the coefficient is 2 gamma omega 1. So I have this. And alpha multiplied by the first derivative. And for the sine, I have minus alpha omega 1, which is this. And I don't have the constant term. Omega naught square multiplied by x, the sine term is 0. So for completeness, I just write omega naught square 0. And the three things add up is also 0. Now I handle the second equation first because it's easier to solve. I can cancel the omega 1. And I immediately find that gamma, from this equation, I immediately find that gamma is just alpha over 2. So I have successfully find the gamma in terms of alpha. Alpha is in the parameter in the original equation. Now I find the gamma in my solution in terms of alpha, which is successful. Now the equation 1 is more difficult to solve, but I can write it now. This is the first term, this is the second term, this is the third term. I write O, okay. And since I would like to make everything in terms of gamma, so I write alpha in terms of 2 gamma, alpha equal to 2 gamma. So this becomes 2 gamma square, okay. Now gamma square minus 2 gamma square is minus gamma square. And I just put it on the right hand side. And I would like to prove, sorry, I just put this minus omega 1 square on the right hand side. So the minus sign is gone. And what is left after taking the square root is omega 1 e to the square root of omega naught square minus gamma square. Again, I have found omega 1 in terms of omega naught and also alpha. Now alpha, gamma is just alpha over 2. So this is just omega naught square minus alpha square over 4, the square root. Okay. Now, so I found the solution of this form. And I have the gamma given by alpha over 2. Omega 1 is omega naught square minus gamma square over 4. And in terms of alpha is given by this. Okay. Now, you can notice that If gamma is zero, this should not be zero. I have a typo here. If gamma is equal to alpha 2, now this time this gamma actually causes a damping in the amplitude. Okay, and you can also see that the new frequency will be smaller than the old frequency, because the new frequency is omega naught square minus gamma square root. So it's smaller than omega naught, because omega naught square minus something square root. Okay, that's something which would reduce the omega naught. So with damping, the frequency is reduced. Okay, that somehow the system moves slower in the presence of external damping. That makes sense, because when you have damping, the things will be getting slower. Okay, so this is the picture. The cosine will give you oscillation, but the exponential factor will give you a decaying amplitude. So it goes like this. Initially, you have a large amplitude oscillation, but eventually it dies down. It oscillates to a smaller and smaller amplitude. It goes like this. Okay, and the amplitude, if you trace the envelope, if you trace the maximum, you will find that amplitude decay with this factor. It is equal to a constant, the initial amplitude multiplied by the exponential decaying factor. So it follows the blue curve. Okay, so this is the resulting motion. Now, we should be careful now. In this problem, we have 2 time scale. In the previous discussion on kinematics, we have a bullet, a ball projected in a viscous medium. We have a release a ball inside viscous medium. Those problems and oscillation, those problems only involve 1 time scale, but we now have 2 time scale. What are the 2 time scale? The first time scale is the time scale for oscillation, typically the period of the oscillation. Okay, how much time it takes for the object to oscillate once, that is a period. But you also have a decay time scale. Say how long will it take for the amplitude of the oscillation to decay by a factor of e to the power minus 1. That is another time scale. So that is characterized by 2 time scale. And for the period T1, that is of course equal to 2 pi over omega 1, right? That is a standard way to find the period of oscillation. You take the frequency, the angular frequency, 2 pi divided by angular frequency gives you the period. And it is useful to characterize the time scale for the decay by the time tau. The time tau is defined 1 over gamma. At this time, the amplitude will goes to e to the power minus 1 of its initial value. So that this 1 over gamma is a time scale for the decay. Okay. So we should define what is light or small damping. Light or small damping is defined as omega naught much larger than gamma. Now, why is it so? Now, for light damping, we actually have the frequency almost unchanged by damping. And the oscillation timescale is much smaller than the decay timescale. What is the meaning of this? Now, the first statement is clear. It means the frequency wouldn't be affected much. It's almost the same as without damping. The second statement is the oscillation timescale is smaller. It means that the object will oscillate many times. It will oscillate many times before the amplitude decays substantially. That is the meaning of this statement. So with a longer decay time and a smaller oscillation time, it means that the object will oscillate again and again for many times before the amplitude is substantially decayed. That is called a small damping. And so you look at the equation now. With this condition, omega 1 is omega naught minus gamma square root. So the gamma can be neglected with respect to omega. And so that is almost omega naught. So that is the first statement here. The frequency remains unchanged. The second thing is that the oscillation timescale is much smaller than the decay timescale. The oscillation timescale is 2 pi over omega 1, right? And since the frequency almost unchanged, omega 1 is omega naught, and the decay timescale is 1 over gamma. Okay, now you see here, if omega naught is much larger than gamma, then 2 pi over omega naught is much smaller than 1 over gamma. So you can immediately see that the decay timescale here is much larger, much longer than the oscillation timescale. And that is the characteristics for a light damping. Now here with some numerical example in order to make things concrete, not so abstract. Now let us take, for example, the frequency, the undamped frequency to be 8. Okay, so I plot the graph with gamma equal to 0.1. Now the 0.1 is a small damping. 0.1 is small compared with 8. Now what is called damping small? The gamma should be more than omega naught. That is called small light damping, right? Now if I calculate omega 1, which is omega naught squared minus gamma square root, I will find that it's very close to 8. So the frequency is almost not effective. You see 7.999, which is essentially 8. So the frequency is not affected at all. But there is a small damping here. So after many oscillation, you can see the amplitude slowly decay. Okay, it just oscillates with a smaller and smaller amplitude as times go on, but it occurs very slowly. Now we increase the damping to 0.4 compared to 0.1 here. You can see the decay is going faster. It's going to 0 faster. The amplitude dies down much faster than here, right? But the frequency still almost remain unchanged. It's 7.98, in fact 0.99, almost 0.99, which is not much different from 8. Although it's closer, but it's not much. It's farther, but it's not much different from 8. So the frequency is almost unchanged also. Now, so let us increase it more drastically. Let's increase the damping to 1.2. Okay, and you can see in this situation that the oscillation just died down in the field cycle. After a field cycle, all the oscillation has gone, and the frequency omega 1 now differs more than the previous case to the original frequency omega naught. Omega 1 and omega naught now differs by 0.1, right? Which is more significant than these two cases. Now, even in this case, you see the difference in frequency is very small. Now we let it make large. If gamma is equal to 3, now 3 is already not small compared with 8. The frequency, the oscillation died down in just one oscillation. After one oscillation, almost all the oscillation has gone. Okay, omega 1 and omega naught, you see the difference is getting larger. Okay, so here we have this numerical example. Now I anticipate you to do it yourself at home for this example. And in the next lecture, we will talk about energy for damping, and we'll also talk about other cases of damping. We'll also consider cases where the damping is large, so that there will be no oscillation at all, and we'll consider those cases. And after that, we will consider a forced oscillation, a simple harmonic motion with a damping and under action of a periodic external force. And we'll talk about the phenomena about resonance, how when the frequency match, the system absorbs a lot of energy from surrounding and become oscillate violently. Okay, so we are going to talk about that in next lecture. Now, so we have the reading week in front. So please take some time to do the review, and just contact me for any time if you like. Okay. So see you later. Any question?